Okay, welcome to another CFE higher electricity video. Today we're looking at internal resistance, and the reason we're looking at internal resistance is because it's an important property of sources of voltage, power supplies, and it's something that we've neglected to tell you so far. So really, it's one of these things where we've been kind of lying to you. So, in the sense that we've been simplifying it until we felt you're old enough to understand. So, here we go. So, this is the idea. If I have a 12 volt battery, as I might have in a car, like a conventional car, petrol car. I know that these other cars, like these, the Teslas and the electric cars, run with very high voltage batteries. That's different altogether. But a conventional petrol or diesel car has a 12 volt battery. If I had a 10 ohm resistor, I'd be measuring 12 volts across my 10 ohm resistor, and I would be getting a current of 1.2 amps flowing through the resistor. And that would be absolutely fine. Cars will do that. Car batteries would do that for days and days, no problem. Now, well, perhaps not days, but they do it for a good while. Okay, now let's look at a slightly different situation where I've got very low resistance. If I have a very low resistance, then you might think that's okay. If the resistance is low, you will just have a much higher current to make this side of the equation multiply up to make 12. And you'd need a current of 120 amperes. But do you think that's possible? Can we really get that? No, there's no way you can get 120 amperes out of a battery for any length of time. And so really, this is the kind of situation you can't have. You can't take large currents from batteries, even if you can spell batteries correctly. It's not an option. And the answer is, why? Now, the mighty George Ohm, he did loads and loads of experiments for years trying to sort out the mysteries of electrical resistance, but was actually held up by the internal resistance of his own batteries and didn't find his law for something like 10 years. So Ohm's law, which we all take as the most basic one, took Ohm quite a long time to work out because he didn't understand this. So we think of each little cell as having a small resistor within it. And so we're going to draw cells as the conventional cell system. And we're going to say that has a magical ability to push electric charge that we call the electromotive force. And that really is a measure of the energy given to each unit of charge as it flows through the cell. Now, we're going to draw the internal resistance of a cell as a small resistor next to, in series with, the cell. And because they're all one thing, we draw this dotted line around them to indicate that is all the cell. That resistor is hidden inside the cell. You never see that resistor. It's just kind of on the diagram to show what's going on. Okay, so the dotted line contains all the cell. Right. And yeah, we use a lowercase r for internal resistance. I perhaps should have mentioned that. On to the next one. Okay, so what is the point of this? Now, if we just look at one of these examples first. In my first example, I've got a 1.2 volt cell with a 0.5 ohm internal resistance. Now, let's look at the load resistor. Now, we often call the core thing that you want a circuit to do the load. The core, it's the thing that the energy from the cell, it's kind of you're hoping that the load is the thing that you want to actually get energy from the cell. So it might be a heater, it might be a light, it might be something, but it's a resistance that generally is taking energy from the cell. You want it to do something. Okay, getting back to the maths. Say I've got a 10 ohm load. As before, now that I've got this resistor in series with the load resistance, my total resistance is 10.5 ohms. So when I do my I equals V over R, I've got 1.2 divided by 10.5, V over total resistance in the circuit, and I now get 0.11 amperes. So if I want to look at the voltage that I would actually measure across this load, I can use Ohm's law again. Now you might be saying, shouldn't he have had the equation at the top? Probably he should. So V equals I times R, and I'm saying VL is the voltage across the load that I'm measuring here. And that is now only 1.1 volts. So you can see that in including this internal resistance, I've lost some volts, but these are volts lost across the internal resistance, which represents energy being lost across the internal resistance. But it's not very much. It's only 0.1 volts out of 1.2. Now, if I go back to my previous type of situation and say, well, that's okay, let's just reduce this resistance. Now my total resistance in my circuit is 0.5 added to 0.1 because my two resistors are in series on my series circuit. So when I do my current, I have 1.2 I equals V over R, V R, 2 amperes. So you can see that now the volts I've got across this device I've only got across the load I times R 2 times 0.2 volts, and I'm losing a whole volt across the internal resistance. So what happens in circuits is you lose voltage to the internal resistance, and the more current you have in the circuit, the more voltage you lose. Okay, so that's let's look at the maths of that now. I've drawn in a little circuit here just to remind you that this voltage and this voltage must add up to the supply voltage. So, should all remember from the previous lesson that those two voltages should add together. Now, let's tidy up my pile of sheets. Let's look at our diagram now. Now, when we're looking at internal resistance, we often say, this is the voltage we're going to lose. And that is going to be the volts lost. And that is often given as the current times by the internal resistance. The voltage across the load is normally given a normal V. And if I try and do the same equation here, I've got my source of voltage. So that was my voltage supply in this basic equation that we've done before. This is my source of voltage here. And these two voltages must add up to that. So I could write this as the electromotive force of the cell equals V plus I times R. Remember, this can be thought of as volts lost. And another way I can write it by taking the IR across the other side of the equation is to write the voltage across the load will be the electromotive force minus the volts lost to the internal resistance. Now I'll just make those I's into I's in case you might mistake them for a 1. So there's a little reminder of the definition, so I don't know if we'll have to come back to this. So I maybe want to put in that is I times little r. And I'm now feeling a bit self-conscious that I haven't got a dotted line around there to indicate that that is my cell. So that's the situation. That's the equation. V equals E minus I times R, and it is just a rewriting of the basic law of voltages that we've got here in this particular situation. So I'm going to go through an example. It's absolutely vital you remember that if you're asked for the volts lost, we're going to go through an example and then we'll stop this video before it goes too long. So, in the circuit below, the battery has an EMF of 5.4 volts. The battery provides a current of 0.3 amps to a bulb. A voltmeter measures 4.8 volts across the bulb. So lots of words, but I prefer a picture. Our task is to find the internal resistance of the battery. So here's my picture. Okay, and if I just hide that bit of math so I don't distract you, we'll just look through the picture. A battery provides an EMF of 5.4 volts. Now again, I've made the mistake of not drawing in the sort of dotted line wrapping around the battery that is traditional and expected. So, and then the battery provides a current of 0.3 amps. So I've marked that in as the current flowing of 0.3 amps there. And the voltage measured across the lamp is 4.8 volts. So, write down my equation. My V is the voltage across the lamp. My E is the 5.4. And my I times R, I don't know R, that's what I'm trying to find. I don't know R. But I know that I times R must be 0.3. And now I just need to solve the equation. So I've decided to take the 5.4, subtract the 5.4 from 4.8 to get it over here, and I get minus 0.6. And I've still got this minus. Then if I take the 0.3 over to the other side, as a divide on this side, and I take the minus sign with it, my minus signs cancel, and I get 2 ohms is R. So my internal resistance is 2 ohms. Okay. So I have, ooh, that was naughty because I've just showed you. I'm going to suggest that you look at homework sheet 13 and try and do questions 6, 7 and 8. And there's a vital hint that in question 6, if you add the EMFs of the two cells together and you add the internal resistances together, it might be easier to consider it as one cell with double the voltage and double the internal resistance. But have a go at those and then we can discuss the answers together.